So we'll start like we normally do. We'll start with the problem. So here we go. For t greater than or equal to 0, a particle moves along the following parametric curve. X is log of 1 plus t squared, y is 1/3 t cubed, and z is arctangent of t plus t over t squared plus 1. And what's the question? Determine the cumulative distance function. All right, so this is what we called last time S of t. In other words, the cumulative means what's the total, the cumulative amount. How much have you accumulated? All right, and where do we start? We start at time 0, which makes sense because our parameterization starts at time 0. And then it says also, well, that means there's a phase 2. Let's finish with phase 1, then we'll get to that also part. So if we're looking for the cumulative distance function, the way we can do this is we can say, okay, that's going to be the integral from 0 up to the current time t. And the reason I start at 0 is because that we're told that's where we want to start measuring. Now, it might be we want to start measuring at a different number. 0 is a very common number because 0, it's a beautiful number. It has wonderful properties. For example, when you evaluate 0, lots of things simplify. All right, 0 to t, and there's a complicated expression, but you can also simplify and say it's the magnitude of r prime of t. So if you remember what r of t is the function which gives position, r prime is velocity, and magnitude of r prime is speed. And therefore, if I want to know my total distance, I integrate my speed. Okay, that makes sense. Good. Well, so what do we need to do? Well, first off, let's write down r of t in our traditional way, because right now it's written not quite in the way we normally would write it. So log of 1 plus t squared, comma, 1/3 t cubed, comma, arctangent of t plus t over t squared plus 1. And so the next step is let's do r prime of t. All right. So, well, this will be good. A nice refresher. All right, what's the derivative of log of 1 plus t squared?
2t over 1 plus t squared.
Ah, good. See, that wasn't so bad. So whenever you have a log, the way you take a derivative is it's 1 over the inside. So that's why you have a 1 plus t squared in the denominator. And then in the numerator, you put the derivative because of the chain rule. So that's where the 2t comes from. How about the derivative of 1/3 t cubed? T squared. All right, that one we can do. All right. Derivative of arctangent of t plus t over t squared plus 1. Well, 1 over 1 plus. Ooh, interesting that there's a 1 over 1 plus t squared there. Very convenient. T over t squared plus 1. Well, all right.
1 over t squared plus 1 plus t over t squared over
Okay.
plus 1 squared.
Someone's doing a product rule. We'll do a quotient rule. We'll go like, extreme derivative rules, like, wow, the quotient rule. And if you're thinking that's extreme, it's like, yeah, look, we're not about throwing crazy derivatives at you. So if you remember the quotient, take the bottom times the root of the top minus the top times the root of the bottom, all divided by the bottom term squared. Now, I just changed the order. T squared plus 1 is 1 plus t squared. Notice that these are almost the same denominator. I just need to have another 1 plus t squared here. So if I wanted to simplify,
I get a mistake in the numerator. It should be t
bottom
plus 1 times 1.
Times the root of the top. You're right. All right. So to get a common denominator, multiply the first term by 1 plus t squared over 1 plus t squared. And let's see, what can we do? All right, so the first two terms we're not doing anything. They look as about as simple as we could hope for. And this last term, well, the denominator, that's 1 plus t squared squared. And in the numerator, we get t squared plus 1 minus 2t squared. And then we're going to add that to 1 plus t squared. And, well, what does that turn out to be? 2. That's right. The t squareds all cancel out because you get a t squared and a t squared and a minus 2 is t squared. Okay, good. At least our derivatives turned out to be not too bad. All right, that's a promising start. So, next up, the magnitude of r prime of t. That's the square root of, well, square the first term, 2t over 1 plus t squared squared, plus square the second term, t squared squared, plus square the last term, 2 over 1 plus t squared squared squared. All right, so we get the following. 4t squared over 1 plus t squared squared plus t to the fourth plus 4 over 1 plus t squared to the fourth. Now, what do we do next? We could pull out a 1 over 1 plus t squared squared, but let's just think about for a second, what's our real goal when we see a square root? Get rid of it. That's our goal. I see a square root, I don't want a square root. And we've been working for like Calc 2, like a good chunk of our classes. Let's get rid of the square root. So with that in mind, what are we looking for? We'd hope there's a perfect square. Now the question is this a perfect square? And remember, what does a perfect square look like? It has the form a squared plus 2ab plus b squared. So the question is this of the form a squared plus 2ab plus b squared?
Well, if you switch the first and the second one, it is.
Ah, see, maybe they didn't give it to us in a fancy order. But see, the cool thing about addition is you can change the order. So someone said, hey, change the first and the second one. So if you did, so if we're thinking of this first one as our a squared, that would be t squared squared. And then if we think of this as our b squared, well, that would be 2 over 1 plus t squared squared. Oh, sorry, there's a square there as well. Lots of 2's here. This is a very 2-y problem. All right, then what would be the middle term? Well, it would be plus 2 times a times b. And then we just check, is it the case that 4t squared over 1 plus t squared squared is 2ab? And I forgot a plus sign here. And the answer is yeah. So it works out. So it's almost as if when this problem was chosen, it would work out to be a perfect square. Now, is that a coincidence? No. We oftentimes choose problems to work out to be perfect squares. Okay, so this is a good chance for us to flex our algebra skills. So it turns out that we get a relatively simple magnitude of r prime. All right, good. Have we found the cumulative distance function? No. What we found is we found the magnitude of r prime. But with that, the next step is not so bad. So we can say that our cumulative distance function is the integral. Oh, I should not use t's here. I should use some other symbol. We'll switch it to tau's. The reason is this t is different from the t that was in there. All right, integral 0 to t of tau squared. You don't have to use a tau. Tau is just a fancy stand-in for t, d tau. All right, can we integrate tau squared?
1/3 tau cubed.
1/3 tau cubed. Can we integrate 2 over 1 plus tau squared squared? Now you might be thinking, I don't know, U sub or trig sub or something fancy. Or you might be thinking, why do we have to do that? We've already done it. You're like, what? When did we do it? Notice that that matches with that derivative. Where did that derivative come from? It came from taking that. So I don't have to integrate it because we've already done it. So it's arctangent of tau plus tau over tau squared plus 1. And evaluate from 0 to t. And when you do this, you'll end up with 1/3 t cubed plus arctangent of t plus t over t squared plus 1. And then you plug in 0, you'll get 0, 0, and 0. And so there is our cumulative distance function. So if you want to say how far have you traveled from time 0 to some other time, plug that time in, and you get the answer. All right, well now we're ready to go on and look at this also. So also find the distance the particle travels between the points log 2 1/3 1/4 pi plus a half and log 4 root 3 1/3 pi plus 1/4 root 3. All right. Well, what does this mean? So we have to figure something out. So how do we figure out our distance traveled? Well, first thing we should do is say, where are we? So for what values of time am I at this expression log 2 1/3 1/4 pi plus a half? Well, let's just say, look at the x-coordinate. I need log 2 to be log of 1 plus t squared. What does that tell me about t? T should be 1. So that says at time 1, I'm at this initial point. Now let's look at this second point. For what values of t am I at the point log 4 root 3 and 1/3 pi plus 1/4 root 3? Well, again, look at the x-coordinate. When does log of 1 plus t squared give 4? Yeah, so t squared would have to be 3. T is root 3. And you might be saying, wait a second, what about negative root 3? Great question. Look at our assumption up here. T needs to be greater than or equal to 0. But we don't want a negative value of t. Okay, so one way we could find the answer is we could say, oh, I just need to integrate 1 to root 3 of magnitude r prime of t dt. And then I'd have to do the work again. But I don't have to do the work again. Because I can say, look, I want to find the distance between the 2 points. So what I can do is I can do something actually a little bit simpler. And I can say, this is the same as how far do I travel when I get to root 3, and I subtract how far I traveled when I'm at 1. So if I look at the cumulative distance function between 2 values of t, this is the distance traveled between the times 1 and root 3. And the thing is that we actually have these cumulative distance functions already. So we don't have to redo any work, we just plug in. So you plug it in. You say, okay, well, when we plug in 1/3 times root 3 cubed, that's 1/3 times square root of 3 times square root of 3 times square root of 3. That'll give square root of 3. Arctangent of square root of 3, does anybody know that? Ooh, close. It's pi over 3. And in case you're nervous, do I have to memorize arctangent of root 3? That would be one we'd probably give you if it was important. But you should know arctangent of 1. All right, and let's see, root 3 over root 3 squared plus 1, that's 1/4 root 3. Then we can subtract, plug in 1. 1/3. And then arctangent of 1. Okay, what is arctangent of 1? Pi over 4. And then 1 over 1 squared plus 1, which is a half. And we can just leave our answer like that. Perfectly fine to leave it that way. All right. Well, any questions on this problem? Okay. Well, so what's our goal for today? Well, we want to get better at understanding motion. So we know we have some basic things. We have r of t is position. And we said, well, you take the derivative of r of t, you get velocity. So we're going to sort of explore this, and then we're going to say, okay, but let's get into acceleration. Then things get more interesting. So when I take the derivative of r of t, I get this r prime of t, and it has two different parts. It has the magnitude, which we just mentioned a few minutes ago. The magnitude of the derivative is our speed. The other thing it has is direction. So we want to come up with something to indicate direction. So we call that capital T. And that stands for what's called the unit tangent vector. So how do you find it? Well, you take your derivative, r prime, and you divide by the magnitude of r prime. And it's always the case that if I have any vector and I divide by its magnitude, I'm always going to get a unit vector. So that's why we call it the unit tangent vector. It has length 1. So when we think about what this represents, this captures the direction of motion because it has the same direction as our derivative, and because we make it a unit vectors represent direction vectors. So that captures the direction of motion. Now, what we can do is we can go back and say, well, what is velocity then? Velocity is a combination of length and direction. Every vector is. Every vector can be written as a combination of the length or the magnitude and the direction that you're going. So let's do an example. So let's find t of t for r of t equals a half t squared root 2t log t. So what do we do? Where do we start? What? Derivative. Right, because t of t comes from the derivative. So r prime of t is equal to the derivative of a half t squared t. Derivative of root 2 times t? Square root of 2. Derivative of log of t? 1 over t. All right, so I found the r prime. The next thing is the magnitude of r prime. So the magnitude of r prime of t is equal to the square root of t squared plus 2 plus 1 over t squared. And this is actually one that we saw before. I think we saw this in our last session. It turns out that this is a case of being a perfect square, because you can imagine the inside term being t times 1 over t. So this becomes the square root of t plus 1 over t squared, which we'll write as t plus 1 over t. Now technically we should put an absolute value here, but I'm going to sort of say, but we have to assume t is positive, and therefore we're okay. Now you might say, how do you know you have to assume t is positive? Well, because it makes it easier for me. But there's actually one other thing that says t has to be positive. Notice this log t at the end. There's no absolute value there. So the only place I can plug in is when I have positive values for t. So, all right, so I can back up what I say. Are we done? Not yet, but we're getting close. By the way, t plus 1 over t is the same as t squared plus 1 divided by t. So if I just put everything over t. So, for our answer, we get that our unit tangent vector, which is r prime of t times divided by the magnitude of r prime of t. That's another way to write that is 1 over the magnitude of r prime times r prime. And so 1 over the magnitude of r prime, I can think of saying, take the reciprocal. So this can be written as t over t squared plus 1 times the vector t root 2 and 1 over t. Now at this stage, you can, if you want, multiply that factor in the front through. So you can say, okay, let me distribute this through. But unless there's a compelling reason, this is also a perfectly valid answer. It's a scalar times a vector, and that is what we're looking for. All right, so that's the velocity. All right, well, what comes after velocity? Acceleration. Yeah, and I think acceleration It's a little bit more interesting. Now, how do you get acceleration? What do you do? Take the derivative of velocity. So that's what we're going to do. We're going to take acceleration, and we're going to say, let's take the derivative of the velocity. And we just said, just a few moments ago, that velocity is this magnitude of r prime times this unit tangent vector. And therefore, I'm going to replace velocity by this expression. And now, let's see what happens. Well, what rule do we need? Product rule. So if you do the product rule, you get the following. It's the derivative of the first term, which is the derivative of the magnitude, times the unit tangent vector, plus it's the magnitude of r prime times the derivative of the unit tangent vector. Now there's some notes underneath there. And it says, you know, you have these two parts here. One part is parallel to motion, and the other part is perpendicular to motion. Now, we have to think about why these things are true, but we'll get into that in just a minute here. So what we'll do is we'll say, okay, I can write this term in front, I'll call that A sub capital T. And then I times it by the unit tangent vector. And this term, I'll rewrite it as A sub n times n. Now, if you think about what we've used, that uses the letter n, how should we think of this n? What other words have we used recently that start with an n? Normal. And so this really is saying perpendicular. So let's justify this claim about being parallel and about being perpendicular. So first off, the parallel is not so hard, because when we're saying something is parallel, we mean it has the same direction. So capital T is the direction of velocity. That's your direction of motion. So what we have is we have a vector which points in the direction of motion times some value, a number. So this is a scaled vector in motion. That's why this part has to be parallel to motion. Now the second part, that one's a little bit more subtle, but it says, okay, why is it the case that the derivative of capital T has to be perpendicular to motion? And now we come back to something we did several sessions ago. Remember when we talked about being on a sphere? Like, imagine like you were on a round Earth. We said, oh, if it's the case that you have constant magnitude, then you are perpendicular to your own derivative. Well, it turns out that a unit vector has constant magnitude. It has a magnitude of 1. And therefore, when I take its derivative, it has to be perpendicular to its current vector. So the current vector is the direction of motion, so its derivative has to be perpendicular to motion, and that's why this part is truly perpendicular to motion. Now, that is not to say that the derivative of t is equal to n. Just because I am perpendicular to a unit tangent vector does not mean I myself am a unit vector. So you have to do a little bit of work. So what's the interesting thing here? We have these two things, a sub t and a sub n. And these really say, let's talk about acceleration, and we're going to talk about acceleration happening in two ways. So if I have a particle moving through space, so here's a particle moving through space, I can think of acceleration trying to do two things. One thing it could do is it could say, all right, I'm going to be pulling you forward. In other words, from the current direction you're going, I'm trying to pull you forward. So it's like, you know, if you have a car going on a straight path, a straight road, doing maybe a drag race. The acceleration, it's propelling you faster and faster in the direction you're going. So that's what the first part is trying to capture, this a sub t times t. But then there's a second thing where it says, hey, I'm going to try to pull you sideways. So there's a second part of acceleration which says, I'm trying to pull you perpendicular to your current motion. And that's what the second part tries to capture, this a sub n times n. So we want to say, okay, how much of my acceleration pulls me forward? How much of my acceleration is pulling me to the side? And so we want to figure out these coefficients, a sub t and a sub n. So that's our goal. Let's find them. And we're going to do them in two different ways. So let's start with just one way. So let's start with basically this picture. So we're going to do an algebraic approach first. Sorry, a geometric approach first. And, all right. There's a lot to process, so let's just work our way through it. So we have our curve, and we're looking at a particular time. So at a particular time, I have my derivative pointing, which is tangent to the curve. And then I have my acceleration, which is pointing, and that's going to be some direction. Almost always acceleration and velocity point in different ways. So I have this going on. And what I can do is I can say, all right, this r double prime of t, remember, this right here is really the acceleration. And I'm trying to get a handle on what's going on. And I can think about the picture. So I come through and I say, let's draw a little triangle. So we take and we dot, 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 dot down to here to make a right angle. And so we can say, all right, the hypotenuse, that comes from r double prime, which is really, again, this is your acceleration. And what are the other two sides? Well, one side here, this side is pointing in the direction of motion. So I can say that the length of this side, that's how much of acceleration points in the direction of motion. And another word we could use here is we could actually talk about projection. So if you projected r double prime onto r prime, you'd have this matrix, this vector. And this is the projection. The other part, well, that's the perpendicular part. So this is the a sub n. So now I say, okay, I have a triangle. I have this angle. It's the angle between my velocity and my acceleration. And I start saying, all right, how do I find the pieces? Well, to find the tangential part, I say if I want the tangential part, that's the side which is adjacent to my angle. And I already have the hypotenuse, that's the acceleration. And the adjacent and the hypotenuse are related by cosine. So the a sub t is the hypotenuse times the cosine. Well, when I see cosine, I think dot product. So I want to make it look like a dot product. And to make it look like a dot product, I need to add a magnitude of r prime, because then I'll have the magnitude of the two vectors times the cosine of the angle between them. So we add the magnitude of r prime, and what do we have? Lo and behold, the top, that's r prime dot r double prime, and then in the denominator, that's the magnitude of r prime. And that's the answer. So it turns out that if I want to know how much I'm moving in the direction of acceleration, I use the dot product. And I've already mentioned this before, I'll say this again. This comes back to projection. So this right here is another way to write the magnitude of projection. So if you were to go through and work it out, that's what you would get. All right, so that's tangential. All right, so the tangential part, that's fairly straightforward. How about the normal part? Well, think about the triangle. I have the angle, and I'm trying to understand the opposite side. So again, I have angle, opposite, hypotenuse. The trigonometric function which relates those is the sine function. So the a sub n, the part that's perpendicular, would be the magnitude of r double prime over times sine theta. Now, when I see a sine theta, what I think about is not the dot product, I think about cross product. Because the sine theta is the term that had a cross product in there. So to make it look more like the actual cross product term, I add, again, this magnitude of r prime. And now I say, aha, the numerator, that is exactly the expression that came from taking a magnitude. Magnitude of r prime cross r double prime. And so, what do we have? We have that acceleration is the a sub t, that's r prime dot r double prime over magnitude of r prime times t, and then a sub n, r prime cross r double prime over magnitude of r prime. Which means if we run this whole process geometrically, we get to do dot product and we get to do cross product. So that's nice. Although, not everyone's a big fan of doing dot products and cross products, especially when you have functions of t. So, maybe it'd be nice if we had it another way. So we're going to talk about finding a sub t and a sub n algebraically, where you don't have to do any dot products or any cross products. In other words, no dot products and no cross products need to be injured. So, how do you do it? So the key thing, there's two key observations to make. The first thing is to come back to what we did over here and say, well, let's stare at this for a second. And if you stare at this for a second, what you'll see is you say, hey, wait a second, this t and this t match, which means that this derivative has to match that coefficient. So I can say that the derivative of the magnitude of r prime, that's my a sub t. All right. Well, that's good to know. So that's the first observation. The derivative of the magnitude of r prime is a sub t. So that's straightforward and easy to find. You can simplify as much as possible, and then you take the derivative to get a sub t. Now, what about observation 2? How do we get a sub n? Well, now, come over and look at the triangle. What kind of triangle do you have? A right triangle. So, if you have a right triangle, what do you want to do to it? Pythagorean theorem. So, we have that the magnitude of r double prime squared is a sub t squared plus a sub n squared. We can find the magnitude of r double prime, and we can find a sub t, because we just did that in the step before, and therefore we can find, oh, that's a typo. I need to fix that. So now we can find, oh, no, that's okay. That is actually correct. Now we can find a sub n. All right. Now you might say, wait a second, do I take the plus or minus? And the answer is you always take the plus. That's just a convention. Okay. A few things to note. There's this comment here, this process works in all dimensions. The reason I mention that is what's true about a cross product. It's a three-dimensional thing. So if you're dealing with a particle that happens to be traveling through dimension 8, you can't use the cross product. But the algebraic works perfectly fine. That's something to keep in mind. So there's a couple of other things to note. If I want the unit tangent vector, we've already talked about that. The unit normal vector, well, we talked about how the derivative of the tangent is perpendicular to the normal. Then you just make it a unit vector by dividing by its magnitude. And I will say, we almost never compute this, just because it is just messy. Very, very messy. But, of course, you can talk about it theoretically. And then there's something called the binormal, which is the cross product, t of t cross n of t. Now, how do I know that this vector is a unit vector? Because I'm not dividing by its magnitude. They're perpendicular, which means that the angle between them is 90 degrees. Because if you think about it, it's, for example, over here, you take the magnitude of the two vectors and multiply it by the sine of the angle. So this will always be a normal vector. What is true about the binormal vector? Well, what's true is it captures the tangent vector, which means we're capturing motion. Because we have t and n, we can put that together, which means we capture acceleration. So the binormal vector would be perpendicular to both r prime and r double prime. Well, something that's perpendicular to both r prime and r double prime is the normal vector to the osculating plane. So that's another place where you can get the normal vector to the osculating plane. But again, that's probably a very hard way to do that. I think that I should make a comment. And there is a strong tendency nowadays to be like, hey, this seems so much easier. Why would we ever go in this route, the geometric route? And the answer is, we can actually construct cases where doing it geometrically is far, far faster than doing it algebraically. So let's just make up an example to demonstrate. All right. You almost never make up an example on the fly, right? Okay. So let's pick an R of t and make it unpleasant. I said make it unpleasant. All right, arctangent. Arctangent of t. All right, what's the next term? Okay. Do you know the derivative of arc cosine? Okay, then we're not going to do it.
E to the negative t.
E to the negative t. Okay.
Sine squared.
Sine squared t. All right. And I'll tack in a 3t here at the end. All right, and suppose I said find a sub n and a sub t at time t equals 0. All right, that's a perfectly valid question. I want to ask, what's happening to these expressions at time t equals 0? Now, if you were to do this algebraically, what would we have to do? Well, to do it algebraically, the first thing is you have to say, well, what is the magnitude of r prime? Well, it would be the square root of, and then you take the derivative of these things, so derivative of arctangent, 1 over 1 plus t squared squared. And then you have to say, okay, take the derivative of e to the negative t minus e to the minus t squared. Then you have to take the derivative of sine squared t, which is sine 2t plus 3 squared. And you'd have to take this derivative. You have to. You can't avoid it. And then from there, you'd have to move on. Okay. Taking this derivative of the magnitude of r prime of t is not, it makes us sad. That's work. What's our goal? We don't want to work. We want to be smart. So, if we do it algebraically, it can be troublesome. Now, the reason that algebraic works nice is oftentimes we'll have something where the magnitude of r prime is very, very clean. And if it's not, we're in trouble. But here, we had this advantage. Notice, we have this at time t equals 0. So that's going to save us some work. Why? Well, suppose I wanted to find this geometrically. All right. Well, let's take r prime of t, and what is that? Well, 1 over 1 plus t squared minus e to the minus t, and sine of 2t plus 3. Let's take r double prime of t. Derivative of 1 over 1 plus t squared. Well, that's minus 2t over 1 plus t squared squared. And then we have e to the minus t, and 2 cosine of 2t. I should. Yes. Aha. Aha. Ha. Yes, I should. But I did. And like, no, you didn't. And I'm going to be, yes, I did. Check it out. Check, check, check. Check it out. All right. Sine squared t. So chain rule, right? 2 times sine of t to the 1 times the derivative of sine, which is cosine. But 2 times sine times cosine is sine of 2t. So I hid the multiplication by cosine. So yes. Yes, you should multiply by cosine, but you can't. In the interest of time, I was trying to speed it up. Of course, now I've lost anything I gained by trying to speed it up. All right. But here's the point. Here's the punchline. See, previously, if I wanted to talk about finding this a sub t and a sub n, I'd have to take the derivative before I could plug in 0. I don't have to wait now. You see, when I'm evaluating at a point, I can take advantage of the fact that I know I'm at a particular point. And so I say, all right, good. So I have r prime of 0. Getting back to where we started. See, the nice thing is when you have to evaluate at a particular point, knowing that you're looking for an a sub t or an a sub n at a particular value gives you power. Because it says, I know I need to evaluate. And the question is, when do you do it? The answer is, as soon as you possibly can. The problem with the other approach was, as soon as you possibly can was very late. Here, it's early. So r prime is 0, 1, negative 1, 3. R double prime is 0 is 0, 1, and 2. So now, the rest of your computations just involve very simple things. So I can take, for a sub t, r prime is 0, dot r double prime is 0, over the magnitude of r prime is 0. Well, so if I take the dot product upstairs, that's 0 minus 1 plus 6. And if you add those up, you're going to end up with 5. Downstairs, take the magnitude of r prime. It's 1 plus 9. So you end up with 5 over square root 11. There's your a sub t. On the other hand, r prime of 0 cross r double prime of 0. And again, now we're dealing with simple vectors. We're dealing with just these vectors. There's no t's involved. And so, okay, I got to get space here. So I, j, k, 1, negative 1, 3, 0, 1, 2. So this turns out to be negative 2i. And then later on we're going to have a negative 3i. And then there's a 0j. And then later on we're going to have a minus 2j. And we're going to have a plus k, and then a minus 0k. Actually, because I'm subtracting, I should pay it as a plus 0k. So I think negative 5, negative 2, 1. Now I did that kind of quick, so what should I do? Yeah, I should check. So I'm always paranoid. All right. Dot product, minus 5, plus 2, plus 3. Oh, that's 0. That's a good sign. 0, minus 2, plus 2, 0. Okay, good. Okay, so it's the magnitude of this negative 5, negative 2, 1 over, and this downstairs we already did, that's square root of 11. So upstairs it's the square root of 25 plus 4 plus 1. That's the square root of 30. Downstairs it's square root of 11. And now we have that's a sub n. And I should specify these are at 0. So there is advantages to knowing both. So yes, the algebraic is oftentimes the fastest way to do it. But if we say, aha, I know both ways to do it, if there are cases where I'm, for example, trying to do it at a certain point, it's much faster to do geometric because I can't avoid having to work with this derivative in the algebraic way. All right, enough theory. Practice. We've got to do it in two different ways just to convince ourselves that it works. Of course we're convinced. It's math. It's always going to work. But it's good to convince. So let's start over here. Let's do it algebra. So the algebraic method. Let's walk through it. Step 1. We want to find r prime of t. All right, for us, it's negative sine t, cosine t, 1. Good. Now, after that, you're going to find the magnitude of r prime of t. So that's going to be the square root of negative sine squared plus cosine squared plus 1 squared. Now, of course, we should be suspicious, and oftentimes we're going to choose examples where things simplify nicely, and this is one of those times. So this is square root of 2. Now we're ready for step 3, which is, what is a sub t? A sub t is the derivative of the magnitude r prime of t. In our case, that's the derivative of root 2, which is 0. A sub t, done. Now, the next thing we go to step 4. And we say, all right, well, what is r double prime t? Because we need to talk about acceleration. So if we're going to talk about decomposition of acceleration, we need at some point the acceleration. Negative cosine t, negative sine t, and 0. Now, step 5 says the following. Let's just do a little quick side note here. Magnitude of r prime is equal to a sub t squared plus a sub n squared. And therefore, we can say that a sub n, if we rewrite this, that's the, magnitude of r double prime squared, a sub n is the square root of magnitude of r double prime squared minus a sub t squared. So, first off, we'll compute the magnitude of r double prime. So, that would be, in our case, the square root of negative cosine t squared plus negative sine t squared plus 0 squared, which is 1. And so finally, on step 6, a sub n is the square root of magnitude of r double prime, 1, quantity squared, subtract a sub t squared, 0 squared, which is 1. So there we go. We get a sub t equals 0, and a sub n equals 1. And, all right, good. Now, nothing terribly complicated. So let's do it again. And this is a problem so nice, we should do it twice. Whoops, almost lost the 1. All right, you cannot lose the 1. So, what's geometric? Well, geometric says you need to start by building up your vectors. So, step 1, you find r prime of t. So in our case, that'll be negative sine cosine 1. And step 2, you should find r double prime of t. Might as well, while you're doing your derivatives, take all your derivatives, negative cosine t, negative sine t, 0. And now the next step, well, the next thing you really should compute is the magnitude of r prime. It's going to show up. So it's the same as before. So negative sine t squared plus cosine t squared plus 1 squared, which is the square root of 2. All right, and now we're ready to do the dot product. So r prime cross r double prime. So in our case, that'll be negative sine times negative cosine. So I'll just say sine t cosine t. Cosine t times negative sine t minus sine t cosine t. And 1 times 0, which is 0. Put it all together, you get 0. And number 5, the thing we need to do the cross product. All right, so that's I, j, k. Negative sine cosine 1, negative cosine, negative sine 0. So we'll get I times cosine times 0. Well, that's not bad. 0. J times 1 times minus cosine t. So that's minus cosine t j. K minus sine t minus sine t. So that's plus sine squared t k. Then minus cosine times cosine. So that's minus negative cosine times cosine. So it's going to be plus cosine squared t times k. We're going to get a minus sine t times 1 times I, but we're subtracting, so that's plus sine t I, and 0 times that times j is 0. So we end up with sine of t, negative cosine t, and then 1. Now, one thing that's true is you can still do the same, check your dot product. So negative sine squared, negative cosine squared, positive 1 is 0. Minus sine cosine plus sine cosine plus 0 is 0. So that rule for checking the dot product is perpendicular always holds, always holds. Now the next thing to check is the magnitude of r prime cross r double prime. I should say the next thing to find. So that's sine of t squared plus negative cosine t squared plus 1 squared, which turns out to be square root of 2. And the last thing is to write down the answers. So a sub t is r prime dot r double prime over magnitude of r prime. So we read off the dot product, and we did that oh, whoops, I put dot cross product when I should put dot. That's a dot. You can see it right there. Big dot, big dot. So that was 0 over root 2, which is 0. And a sub n, which is the magnitude of r prime cross r double prime, over the magnitude of r prime, is root 2 from here, divided by root 2 from there, which is 1. So we get a sub t equals 0 and a sub n equals 1. All right, well, it's true. Maybe not the most convincing. That's all right. We'll do some more. And hopefully, soon, we'll be convinced. Or at least we'll be convinced we can do it. Find a sub t and a sub n for r of t is sine t minus t cosine t plus t sine t, and t squared minus pi squared. So let's do this one. Let's do this one algebraic. They're the same. So, at least when I say they're the same, they'll get the same answers. So, we start. What is r prime of t? Well, that would be derivative is cosine t minus product rule cosine t plus t sine t, then minus sine t plus sine t plus t cosine t, and 2t. 2t or not 2t? It's not 2t. There we go. All right, cosines cancel, sines cancel. So we get something rather nice. T sine t, t cosine t, and 2t. So the magnitude of r prime is the square root of t sine t quantity squared plus t cosine t quantity squared plus 2t quantity squared, which if you look at that, you get everything has a t squared in it, so you get a t squared, sine squared plus cosine squared plus 4. You get a 4, sine squared plus cosine, or sine squared plus cosine squared equals 1. So that's square root of 5. So you end up with square root of 5 t. All right, good. So a sub t is the derivative of the magnitude, which means it's the derivative of square root of 5 times t, which means square root of 5. All right, so this is a little different. Last time we had a sub t was 0. This time, that's square root of 5. All right, well, that's fine. It's got to be something, so why not square root of 5? Now, that's our a sub t. Next level, you got to go and get r double prime. So r double prime, what does that turn out to be? Take the derivative. You're going to get sine t plus t cosine t, and you're going to get cosine t minus t sine t, and finally you'll end up with 2. So we need the magnitude of that, and so we're going to get the square root of sine t plus t cosine t squared plus cosine t minus t sine t squared plus 2 squared. I guess I didn't need that much space, but I'll need it soon. So sine squared plus 2t sine t cosine t plus t squared cosine squared t plus cosine squared t minus 2t sine t cosine t plus t squared cosine squared t plus 4. Now, if we start looking at this, we'll see we've lived a good life because nice things happen. Sine t, cosine t terms cancel. Next, you'll see we get a sine squared plus a cosine squared plus 4 more. All right, well, that gives us 5. So we get square root of 5. Well, what's left? Well, what's left, t squared cosine t, t squared. Oh, no. I have not copied this right. This should be squaring there. Oh my gosh, check your work. See, look, I knew something was wrong because I knew things should be nice. And knowing that things should be nice can say, hey, if things aren't nice, check your work. See, I squared it, but I was in like cosine mindset. No, that should be a sine mindset. All right, good. Well, anyways, t squared. So that's 5, square root of 5 plus t squared. All right, so where are we at? Well, the last thing is to do a sub n. So remember, that's the square root of magnitude of r double prime squared minus a sub t squared. Well, that's the square root of 5 plus t squared, because when you square root and the square, they cancel. Minus, well, we want to square the square root of 5, so we end up with the square root of t squared, which is simply t. So, a sub t, we get square root of 5, and a sub n, we get is t. All right, good. We didn't have to take a dot product or a cross product. We could have, but we didn't have to. All right. One more. Find a sub t and a sub n, where r sub t is this expression, e to the t plus 17, 2e to the negative t plus pi, and 31 minus 2t. All right. Well, we've done, the last one was algebraic. We'll do this one geometric. So we have r, let's do r prime. So r prime, well, that'll be e to the t. Then the next term, minus 2 e to the minus t. And the last term is minus 2. All right, well, we're taking derivatives, r double prime. That'll be e to the t and plus 2e to the minus t. Last entry, 0. Gone. All right. What do we need? Well, we need to know the magnitude of r prime. So magnitude of r prime of t, that's the square root of, square each term, that'll be e to the 2t plus 4 e to the minus 2t, and then plus 4, because we square things so negatives become positive. Now this can actually, and this won't surprise you, we can rewrite this as e to the t squared plus 4 plus 2e to the negative t squared. And really what happens here is this 4 becomes 2 times e to the t times 2e to the minus t. So it's just of the right format. So it's the square root of e to the t plus 2e to the negative t, quantity squared, which means our magnitude is pretty simple. E to the t plus 2e to negative t. Good. Now, doing the geometric part, well, we need to have r prime dot r double prime. So e to the t times e to the t, that would be e to the 2t. Minus 2e to the minus 2t times 2e to the minus t would be minus 4e to the minus 2t. And then minus 2 times 0 is plus 0. All right, so there's that. Now, r prime cross r double prime. All right, I, j, k, e to the t, minus 2e to the minus t, minus 2, e to the t, 2e to the minus t, 0. And what do we get? I times nth term times 0, that's 0. J times minus 2 times e to the t, minus 2 e to the t j. K times e to the t times 2e to the minus t, so that becomes plus 2 times k. Now, going the other direction, e to the t, e to the minus t cancel, there's a minus 2, but because we're going this way, minus minus 2 makes plus 2. 2e to the minus 2 times minus 2 is negative 4e to the negative t. In the I direction, we're subtracting that, so it becomes 4e to the negative t. And we have 0 e to the tj, so that's 0 in the j direction. Which means that the cross product produces 4e to the negative t minus 2e to the t and 4. And again, you can always check. So here we get 4, here we get plus 4, and here we get minus 8. That's good. Here we get 4, here we get minus 4, and then we get 0. So yeah, it works out. Good. Good. All right. What's the magnitude here? Magnitude of r prime cross r double prime. Well, looks tough, but wait a second. Let's take a look at something. Notice this is the magnitude. These terms, I can pull out a 2. So I get 2e to the minus t, I get minus e to the t, I'm left with 2. And if you look here at these terms, and compare it to the r prime, you'll see, okay, I got e to the t, I got 2, and I got minus 2e to the minus t. So really, this is like you took the r prime, but you kind of jumbled it up a little bit. Not much, but just enough, and negated things. Well look, doesn't matter the order, doesn't matter the negation. So it turns out, this is going to be the same as just the 2 from here, times this same expression, e to the t plus 2e to the negative t. And now, we're almost done. Okay, so what is our a sub t? Well, a sub t is e to the 2t minus 4e to the negative 2t divided by e to the t plus 2e to the negative t. And a sub n, well, that's 2 times e to the t plus 2e to the negative t divided by e to the t plus 2e to the negative t. Now you might say, I bet you we can simplify this because I see cancellation. I see that cancellation going on. Well, you're right, that cancellation happens. A sub n is in fact 2. There's another one, do you see it? Upstairs. See, that's e to the t quantity squared minus 2e to the negative t quantity squared, which means I have a difference of squares. So if it's a squared minus b squared, I can write this as a minus b, and then I can multiply as a plus b divided by e to the t plus 2e to the negative t. And now you're like, whoa, these cancel, which they do, which means that our a sub t is e to the t minus 2e to the minus t. So, final answer for part A is a sub t is e to the t minus 2e to the negative t, and a sub n is 2. Now, let's switch gears because we still have to answer part 2. So what's part 2 say? Well, when is acceleration perpendicular to motion? So what does that mean? Well, that says, hey, if I look at my acceleration, what needs to be the case is that nothing is going with motion. In other words, if I have my motion says this way, acceleration, I want it to be at a right angle. That's what I want. So if motion goes this way, acceleration, right angle, well, that would say that really we can rephrase this in saying that the amount of acceleration in the direction of motion, or this coefficient a sub t, is 0. So we come over here, we say, well, that says e to the t minus 2e to the negative t has to equal 0. And we start moving things around. That's e to the t equals 2e to the negative t, which is really just a way of saying 2 over e to the t. So we can then multiply, we get e to the t times e to the t, which is e to the 2t, is 2. Take the natural log of both sides. 2t is log of 2, or t is 1/2 log of 2, which you could also say is the log of root 2. So there's our answer for the second part. So perpendicular to motion at time t equals log root 2. So all right, algebraic, geometric, they're both beautiful because math is beautiful.